I'm going to try and keep this interesting because I don't want to fall asleep. So this is a joint work with a number of folks. Fitz is a graduate student at Yale. Nabeen was an undergraduate student of mine at FNM. Obaid is a postdoc who's now at Yale, and Brian is at Yale as well. And we all happen to like beer, which explains the logos. So that's the project webpage, if any of you is interested in looking at all the related work that goes with this. So I'll start with what happened a long, long time ago, well before I was born. Maybe there were some of you who were still there, and TCP was the internet workhorse. It was built as the internet workhorse. It had reliable, ordered, connection-oriented byte stream, and it had flow control, and it had all kinds of good things that were built into it. And there was UDP as well, which was essentially built as a transport no-op. Always a transport no-op. And you might argue that it demuxes, but yeah, big deal. My 5-year-old can do that. Applications are largely happy. TCP sufficed for the most part. FTP, Telnet, email were the killer apps, of course, and everything was good. UDP was designed for simple messaging. DNS and TFTP were the ones that used it, but that was the state of the art. And then eventually, over several moons, TCP continued to mature. We built a lot of things into it. We got congestion control. We got ECN to do better congestion control, smaller buffers, and so on. And we have MPTCP coming up next in about 25 minutes. For multiple interfaces. So TCP has continued to keep moving forward, and UDP has continued to remain a no-op because it was always a no-op. It didn't have to go anywhere. And with this state of the art, applications, as time progressed, weren't necessarily happy with the services that were continuing to be offered. TCP services of being a byte stream, reliable ordered byte stream, was insufficient, and a number of applications like real-time audio-video communication, multimedia streaming, and the web found these services to be limiting. So new transports were built in response. We built a number of them. We wrote a lot of RFCs. We did a lot of standardization work, new bits, excellent, all good work. We built SCTP, which gave multi-streaming, message boundaries, multi-homing, partial reliability, congestion control, a whole bunch of good jazz. DCCP was unordered and gave us congestion control over an unreliable datagram stream, which was fantastic as well. And we had some research proposals, SST and POC, and maybe some of you may cringe, but Beep is sort of falls in the same space as far as I'm concerned. But yeah, we built a lot of good bits on the wire. The internet, however, didn't like that so much. Remained loyal through this. What do I mean by this? Well, TCP and or UDP are the only ones that get through most middle boxes. And only TCP gets through all middle boxes, and oftentimes only as HTTP or HTTPS. And this is very much the state of affairs right now. The new and unknown transports rarely get through. So we can build new bits all we want. They're just not going to get through the wire. How deep does this loyalty run? So when I say that there are middle boxes that only TCP and or UDP get through, what do I mean by these? What are these middle boxes that I'm talking about? We've heard about some of these here already. We're talking about NATs, cheap and ubiquitous, all over the place. Everybody has them. Nobody is going to upgrade their firmware. Firewalls, which run often on TCP UDP, that have policies based on TCP UDP port numbers, and sometimes DPI as well. And then there are these performance enhancing proxies, or you may also have heard of them as WAN optimizers and other such, which essentially improve TCP performance. And UDP, again, is largely a no-op in these devices. So with the internet remaining loyal to these protocols, and with us building brand new transport protocols that really don't get used, how did applications cope? What do? Well, they go ahead and build their own abstractions. That's what they do. They build their own abstractions on top of TCP and UDP because it works. Those are the things that actually work. They get through the network. And this started way earlier, right? HTTP with the web, browsers opening multiple connections because they want parallelism. And they like multi-streaming, but TCP didn't offer that. And we built it in other protocols, but they didn't really get deployed. And so they built congestion control and retransmissions on UDP because they want some reliability, maybe not all. This comes at a cost, however, right? Abstracting on top of UDP, eventually, within a few iterations of design and building, tends to look like TCP on top of UDP. And this has happened several times, except we don't really see this code because it's hidden away inside applications, or it's hidden away in application libraries, where you see similar things, like you see retransmission timers, you see reliability, you see congestion control, or at least bandwidth measurement techniques that are built into these applications. And this can also interact poorly with UDP's service model. Now, what do I mean by UDP service model? I don't just mean the Datagram API. I mean also with NATs and other middle boxes that look at a UDP datagram, and they don't associate any connection type state with them. So if you have a NAT, for example, the amount of time for which it's going to hold state for a UDP is much lesser than the amount of time for which it holds state for a TCP connection, because with TCP it expects to see a fin at the end. With the UDP connection it doesn't. So you have to, the application or any library that's abstracting on top of UDP, if there is the notion of a session, will have to keep alive and so on. Similarly, abstracting on top of TCP also comes at a cost. And the most important cost is the buffering and the latency cost. And this is sort of the thrust of the talk here, is that the cost of abstracting on top of TCP is buffering and latency, and it is a cost that we can't afford to live with. We can afford to live with some loss of bandwidth because we can abstract and get more bandwidth. We can't abstract and reclaim time that's lost in the stack. So abstracting on top of TCP adds buffering and latency, and it can also interact poorly with TCP mechanisms. We've seen this again with HTTP, where opening up multiple connections for parallelism, there are trade-offs. If you open up too many connections, you lose performance because TCP works well only for large data transfers. So we have applications that are abstracting this way. We have transports that we build that are not getting deployed. What's our response? What has our response so far been? Well, we started off with saying NATs are evil. We don't care about them, right? And so we'll keep building what we do. And then we said it'll all change with V6, as everything will, of course, the day V6 is deployed. And then we said, well, don't design around middle boxes. We'll encourage them. We don't want them to get deployed. They're already there. Let's kill them. And then we said, wait. They're getting deployed. We can't do anything about this, but we can start designing them, right? And we'll tell them how they ought to be built. And then eventually we realized that didn't work either. So we said, why build a new transport? It's not going to get deployed. Let's just overlay everything, right? So we started with denial. We moved on to anger. We went on to bargaining. And then we ended at depression. And if you know where I'm going next, this talk is about getting to the final stage. I think the depression is based on something real, but we ought to empower ourselves and take charge of this. So we come up with these new design assumptions for end-to-end services, the most important ones being that middle boxes are here to stay. They're not going away. And design should not require any changes to middle boxes. We can't expect them to change before we can deploy anything new. The most important consequence is that new end-to-end services must look like protocols that have already appear as legacy protocols on the wire, so that they actually are deployable through the network as it is, not as we would like it to be. So the Minion suite, which is the paper that I'm talking about here, is a packet pack horse for deploying new transports. That's how we see it. It essentially uses legacy protocols, TCP, TLS, and UDP, but it uses them as a substrate. It builds them as things on which you can abstract, and it eliminates the costs of abstracting on top of these protocols. So it turns legacy protocols into minions that offer an unordered datagram service on top of which you can build new transports. And so we want to build new services that applications really want on top of this substrate that we are offering. So I'll talk about, basically now I'll talk about what Minion exactly is, how we how we build unordered delivery in TCP with Minion, and in particular with UCOBs, and how we do this with TLS as well. And I'll talk about that very briefly. I'll summarize that piece, and I'll show you some impact on some real applications that we've built with this. Okay. So what's the Minion suite? The Minion suite is basically some extensions to TCP that are in the kernel under the red line as you see there, under the operating system API. And it's a bunch of things that we put up in user space. I'll talk about these pieces soon. And above these two pieces, we get the blue line, which is the Minion API, which we offer to applications. This is the richer API that we want applications to be able to use. The key point here is that applications don't really care what the bits on the wire look like. They care about services that they get. And so our job here with Minion is to make it possible to offer those services and allow for the right type of protocol to work on the wire. So we can use TCP if that's the only thing that's supported. If we can use UTCP, which I'll describe in a moment, it's our modification to TCP to allow for unordered delivery. Or we can allow for DCCP if it actually works in the network. If that's the right thing to use, then that's what we use. That's what we'd like to build. What this talk is going to focus on, what the paper focuses on, are essentially UCOBs and UTLS and how we build those pieces. So our goal with the Minion suite is to break up the functions of the transport layer into pieces which we can compose. And the pieces that we use to compose them, we try to remain compatible with the network and with end hosts. This is based on the transport logjam paper that we published in Hotnets in 2008, and we have a longer version of this paper languishing. But that's the intellectual basis for this work. So here in this talk, I'm going to focus on UCOBs and UTCP, and I'll summarize very briefly in one slide UTLS, which is unordered message delivery that looks like TLS or SSL on the wire. So this is the Minion. So we'll first start with UTCP, which is the kernel component of the Minion protocol suite, and we'll go on to the other pieces after that. So what is UTCP? UTCP is basically unordered TCP. I'll let that sink in for just a moment, because it doesn't really make sense, but I'll let you work with that anyways. We introduced two new socket options, TCP socket options. What are the two new TCP socket options we introduced in Linux? The first one is at the receive side, which is simply SO unordered receive. What this does is it makes the kernel deliver incoming data immediately without waiting to see if it's in fact in order or not. So it's sort of like hitting, well, I'll use this analogy later, but this includes in order and out of order data. So any data that comes in just gets shipped up through the socket interface. And we also deliver the TCP sequence number so that anything that's sitting in user space can actually make some sense out of this, because this is just data that's coming out through the sockets interface. And I'll talk about how we actually use this information shortly. The unordered send is at the sender side. It's a separate TCP, it's a separate socket option. And the unordered send call allows for applications to specify a priority with every message that is shipped into the kernel. So these messages that come down from the application are placed, in our case, in our implementation, in a priority queue in the send side socket buffer. And this is done only for the untransmitted data. As soon as data gets sequenced and sent out on the wire, we cannot touch it, because at this point it has been serialized, and now it's in TCP's world. It has to be in TCP's world, it has to be in a FIFO queue. So that's okay, but we maintain the rest of it, the data that's queued but not yet transmitted, we maintain that in a priority queue. Right. So I'll show you what I mean by delivering everything as soon as they arrive at the receiver. It's basically, this is standard TCP, right? There's the kernel under the red line there, and there's an application that issues a read call, and data that comes in order, the QMAC point here is 101. So the data that comes in with sequence number 101 gets delivered immediately and goes up and joins the application receive buffer, and everybody's happy. As soon as there's a loss, however, as soon as there's data that comes in after a gap, any read does not return anything because the TCP stack is waiting for the gap to be filled, which when it gets filled, gets delivered along with whatever data was queued in the out-of-order queue. That's standard TCP. The way we modify this at the receiver is as follows. When data arrives in sequence, it gets delivered in much the same way as it did before, except with one small change. We deliver the sequence number up as well. We actually don't deliver the exact sequence number. We deliver the difference from the beginning of the data stream, but that's a minor point. And when data arrives and goes into the out-of-order queue, we also deliver it up to the application. And then eventually, when data comes in and fills the gap, that also gets delivered. And we might also have, in this case, 301 get delivered as a duplicate up to the application. We sort of just want to open up TCP and have all the data come up so we can deal with it. That's our goal. So with this kind of data, what we have here is basically, it's almost like you've hit oil. You're walking in the desert and you hit oil. And now you have things coming out, right? And you need to build some stuff on top of it to actually make sense of this data that's coming out, because that's what you have here. You have duplicates coming out, you have just data blobs coming out, which don't have any meaningful boundaries, and you have to make sense out of this. So that's what we do with UCOBS, which is the piece of the user space library that sits on top of COBS. So what does UCOBS do? Well, the byte stream has no inherent structure in it. TCP segments don't inherently mean anything because network middle boxes can resegment and we can do all sorts of different things, and we don't want to constrain how segments are built. So we need a separate message framing mechanism to actually detect messages in arbitrary stream fragments. The application, UCOBS, sitting in the application, when it's getting stuff out of this TCP socket, is getting basically stream fragments. It's getting pieces, right? And we want to be able to detect messages in them. This is what I mean by unordered delivery. Unordered byte delivery doesn't mean anything, but unordered message delivery actually can have semantics. So to be able to deliver messages from arbitrary byte blobs that we are receiving from the kernel, we need to have a framing mechanism that allows us to detect messages in these arbitrary byte blobs. And for doing this, we use COBS, which is a self-delimiting framing mechanism. This was published by Stuart Cheshire in SICOM 96 or 97, I think. And it's a really cool, very, very cool encoding mechanism that basically takes out a delimiter byte. So if we use 0 as a delimiter byte, we take a message, we slap zeros at the two ends, and we use COBS encoding to eliminate all the zeros in the data. So it's essentially a very cool escape mechanism, right? And the reason it's very cool is because it gives us a maximum bit overhead guarantee. It's 0.4%, which is really not bad. It's about 6 bytes for a 1500 byte packet. So we can surely leave that space when messages are going down, COBS encode, slap zeros, and ship it down. And that's exactly what we do. So on the send side, we take messages, we COBS encode them, slap zeros, ship them down into the socket, and we also attach a priority to each of these messages so that they go into the priority queue in the TCP send buffer. When it goes through the TCP, so when it goes through TCP and it gets received at the receiver, when data comes out at the receive side, the UCOBS library implementation basically pulls out these out-of-order messages anywhere in the byte stream. It can pull them out, it extracts them, it decodes them, and it delivers these messages to the application sitting above. So what we have achieved here is we've built essentially a truly unordered datagram service, which is still reliable because TCP has to do what it does to remain compatible with middle boxes in the network. But we have achieved unordered delivery with prioritization at the sender through a connection. 5 minutes, thank you. 5 minutes for me to finish talking or for the whole thing? Okay, good, perfect. So, UTLS, I'll very quickly summarize this. The details are in the paper, but the idea here is that we use SSL or TLS encoding. We use the same encoding. We don't change this. So this is truly, truly indistinguishable from TLS on the wire. COBS at least transforms the data. So if you put an HTTP packet through COBS, it's transformed. So it doesn't look like HTTP, it's COBS transformed. But TLS, with UTLS, we don't touch the frame format at all. It's exactly the same frame format. But we are able to do out-of-order delivery at the receiver using the TLS frame format itself as a framing mechanism. And we address the key challenges in there. And we describe this in the paper. I'm not going to go into this right now. So the implementation that we have is in Linux 2.6.32. And we were able to do this by modifying 565 lines of kernel code. And this was done, at least a good chunk of it was done by some undergraduate students. So that tells you how complex it needs to be. The user space library for UCOBS and UTLS was built it's built as a user space library and can easily ship as a part of applications. The UCOBS library itself took about 732 lines, and UTLS, which was implemented as a modification in OpenSSL, took about 586 lines of code. So it's not a huge amount of code, but if you want to optimize, you'll want to do some more work. But at least you can build a prototype quite well. I'll show you a few pictures to show you that this actually works. So this first one is simply a functionality graph that shows that we can do unordered delivery with Minion. So what this shows here is the time at which messages were received at the receiver on the x-axis, and the y-axis shows just a message sequence number. So you can see the green curve is the standard TCP curve as it's seen from an application. There's a loss rate here, but this is TCP underneath the application just receiving data. And when there's a loss, there's a pause. That's what's seen as the horizontal green dotted line. And then suddenly everything gets delivered up in a burst, right? Whereas with the red line, so what you see with TCP is basically these horizontal sort of long pause periods at the application. But with the UTCP and with UCOBS on top of it, you get these nice regions where data doesn't get held up in the kernel, it's delivered up, and when data gets retransmitted, we get those as well. So with message priorities, we get something really cool, and this is something I want to spend just a minute on because this was somewhat of an unintuitive result, but not unintuitive actually, it was a surprising result, but it makes complete sense. This is an example where an application where every 100th message is a high priority message, and all other 99 messages are low priority messages. So it's an application that is shuffling two streams, so to speak, and there's some sense of latency that it has. Some data is latency sensitive, some is not. And when you send both of these data pieces over a single TCP connection, you can't really do much. You get FIFO queuing, right? You can't really tell TCP I have high priority data going into the queue. It doesn't make sense. So you would expect to see that with TCP, the latency observed by both of these different types of data that are semantically different to the application are essentially the same, and that's what you get. But you get different properties with UTCP, and that's what I want to show here. This is a little confusing, but very quickly, the red and the green curves, if you can see them there, that overlap each other, are essentially, this is a latency graph for messages just over time on the x-axis and the end-to-end delay measured at the application on the y-axis. So the red and the green curves that overlap each other are just seen, these messages on TCP. But when you use prioritization and you use UCOBS, you get the blue curve for the low priority messages, which looks exactly like TCP, and you get the really cool black curve down below. Because what happens here is that as soon as an application sends a message down and says this is high priority, our priority queue bypasses the entire send buffer, and this message hits the head of the send buffer, and around this time, there's an acknowledgement coming back on the TCP connection for the low priority data that was already in transmission. And this pulls the high priority data and delivers it immediately. And even if there's a loss, it gets retransmitted very quickly. So that's our just a micro benchmark again for how message priorities work. Why do we care to build something like this? There's an instant karma for building this. You can actually use this with applications as they are. We have applications right now that could use this. Video and voice conferencing and interactive streaming applications can use this immediately. You can do much better web browsing because you can actually get parallelism, true parallelism. When you have unordered delivery, you can build partial order on top of that, and you can get true parallelism. And the other really cool one that we figured out was that you could change the delay properties of a TCP tunnel or an SSL tunnel by using this, and therefore give better performance to TCP connections that are going over or through a tunnel. There's medium-term karma, where applications that are starting to build new applications that are coming up essentially will have Minion services available at design time. So they'll be able to choose among the other services that they have Minion services as well. And finally, there's the reincarnative karma, and as always, you have to sort of believe in it for it to happen, right? Is that this can be somewhat of a next-generation transport abstraction, that we have now an abstraction that has low cost, or at least minimized its cost, but retain network compatibility, and now we can build other abstractions on top of this and maybe even standardize them. So I have some impact on real applications. I'm not going to go through them because I'm out of time. And these are in the paper, however, and let me skim this. This is basically latency graphs for different applications. And I conclude by basically saying that TCP and TLS work. We know that they work. We use them. We have mature performant implementations that have been around for donkey's years. Well, there's a donkey. And they are increasingly being used as substrates. I actually just made that connection right now. And they are being used as substrates. And the point here is that we have to think about, when we think about the cost of abstraction, latency is one of the most important costs that tends to get overlooked, but it is the one cost that if you bury it in, is really hard to pull out. And if you bury it in, there's no way to abstract and take it out. So we have to think about latency when we're abstracting. Bandwidth will always get more. And we can fit square pegs through this round pipe. We can abstract well, and we can actually turn these workhorses into pack horses. Thank you.
Great. So one protocol that I've wanted to build in applications and have from time to time over UDP is the idea of canceling previous messages and replacing them. Obviously, if they've already been queued at TCP, this can't be done, but I assume it would be straightforward otherwise. Have you thought about the fun things you can do?
So yes. So we did think about what else we could do, but retain the TCP headers and so on. I want to point here to a paper last year in IMC 2011 that was showed that you really, there are a number of things that so, okay, I'll step back and I'll answer this question differently. We are constrained, the hard constraint that we worked with here was that we didn't want to change the wire format of the TCP protocol at all. So if there are middle boxes that actually retain TCP state, that are actually IDS boxes, for example, that are looking at inspecting data and seeing if a transmission is different from a retransmission, you trip them up if you did something like that. So we used our constraint was to not change anything in the TCP protocol on the wire as it was. We just wanted to change everything that we could do within the end hosts. One other nice thing that this gets for you is that now you have a nice clean separation between the sender and the receiver. So even if the receiver does not support UTCP, we can still get benefits. So you don't need to negotiate a different version of TCP at all. Go for it.